It's time we talked about a difficult issue. Bias. Now I know that perhaps within every household, if you've got brothers and sisters, or even amongst your friendship group, you've talked before about bias. I know that I've accused my mum, my dad, my siblings before of being biased and showing favouritism to one option over another. But what is bias within mathematics? Okay, well, we'll define it as when the probability of an outcome is not as it should be in a fair situation. So when things are not as they should be. So let's have a look at a series of 5 different dice and let's decide if you think any of these dice are biased. So if the outcomes are not what they should be. Now what I'm going to record in the table is the relative frequency, which is how often things happened. Now if you remember back to part 2, we investigated what happens with dice and coins. In particular, we looked at coins with heads and tails, and we found that over time, if you do enough trials, the probability tends towards half. The relative frequency becomes the theoretical probability. Well, that's going to be really important for this. So the first dice, I got 5 heads and 1 tails. The second dice had 12 heads and 8 tails. So that one was thrown far more times. The third one had 33 heads and 15 tails. The fourth one had 82 heads and 90 tails. And the fifth one had 1,103 heads and 1,087 tails. So each of these dice were thrown a very different number of times. And what you're going to now try and do is look at the 5 scores and see which ones you think are biased. So what I suggest you do now is pause the video, talk to the person next to you if this is in class, and decide whether or not you think the numbers are suspicious. Now the first thing that comes to mind, hopefully, is that you're expecting half heads, half tails. Pause the video now then, if you wish to have some time in order to decide which is biased. Okay then. So the first dice was only the first coin was only tossed 6 times. 6 times. That's a tricky one really, because if it's only been tossed 6 times, we haven't got many results. And if you remember, our theory from part 2 was that as the number of trials increases, the relative frequency becomes the theoretical probability. So we expect things to look more accurate when we've done more trials. So, dice number 1. 5 heads, 1 tails. Well, it's not very even, is it? Difficult here. I would rule for the first dice that it's not possible to tell, on the grounds that we've only got those 5 trials. We would need more data than 5 in order to make a confident decision. Now, if you'd said it was biased, because 5 out of 6 is quite a lot, I can understand that. If you said it was unbiased, the reason you'd have to give, based on what we know, is that it's not enough trials. So, dice 1, not possible to tell, is the judgment. Okay, what about dice 2? Well, 12 out of a total of how many were heads? 12 out of 20, which is only slightly more than half. So I would say that is unbiased. You may disagree. The next one, 33 out of 48, is quite a lot of heads. Just a reminder of how we get the percentage. Put it into our calculator as a divide, and that's 69% heads. So I think that's biased. If there were 48 in total, what should it have been? It should have been 24 and 24. So it's quite a long way out. Now, 82 to 90 is 8 out. But as a percentage, 82 divided by 172, 47.6%. Do you know what? I'm going to call that unbiased. And the last one, even though the gap here is 26, which is more than here, it's only 50.3%. So I think that's unbiased. And my justification would be these figures. That one was 60%, but it was very few trials. 69% for quite a lot more. Then it went nearly 50%. And if you remember, as we do more trials, it should get closer to accurate. So to jump from 60 up to 69% is a lot. Okay, let's do the same thing now with a dice. Apologies, that should have said coin. Here are the scores for a dice for each number. I want you to decide whether or not you think the dice has bias. I want you to think about the method we used over here. And come up with a calculation for each one. So pause the video now to attempt this. So, the total frequency was 80. How many of each would I expect to get then? Well, 80 divided evenly between 6, which is assuming it's fair, is 13.3, recurring. So I should have got 13.3, 13.3, 13.3. Pause again now to try and work out how you would write up your case here with your decision. So here's my answer and justification. And remember, it's always about how I justify, how I explain. This die is biased, I believe. 3 occurs far too much and 4 too little. The rest appear around expectation. The die is biased towards 3. Now, for those of you who know what a die is like, let's use the die rather than this. Here is the number 4, the poor, rarely occurring number 4. What's on the opposite side? It's the 3. So 3 and 4 are opposite. 1 is opposite 6. So 2 and 5 are also opposite. So if I was to try and give a really complicated answer, maybe there's something in this dice that weights towards the 3 side rather than the 4, but it doesn't weight the other pairs. Each was expected 13 times. This sentence here is crucial because if I hadn't written this down here, which I know you'd have done, there's no explanation on paper for what I'm saying here when I say that 3 occurs far too much and 4 too little. So I hope you found that clear. Look at what's expected for each option, for each outcome, and then compare that to what happens. That's route 1. The second one is to work out the relative frequency and compare it to the theoretical probability. So if I expect something to happen 20% of the time and it happens 40% of the time, is that realistic? Well, the answer is it's up for you to decide, and the number of trials may make a difference. But now you know the key things to consider: the number of trials, the expected values. In the next part, we're going to look at independent events and then build into the very tricky topic of tree diagrams.